Hello everyone and welcome back to another video on physics, and this time about Coulomb's law. So this one is going to be an in-depth concept, but it's going to be a really short one because isn't really a very hard topic. So open your mind going into this. Coulomb's law is what we discussed in the previous video. So like we mentioned in electrostatics, we're analyzing two different charges. So for example, let's draw them again here. We'll have two charges and they're not going to be moving. Whoop, that's not what I meant to draw. Right there. They're not going to be moving and they have polarity. Polarity means that they have different charges or they have a designated charge. Now, these two are going to be they're not moving, they're going to be static, and we can predict how they're going to move because of their signs or polarity again. So we know that unlike signs, they attract, so they're going to be going towards each other. And this is what we call attraction. On the other hand, if for example I decided to make this a positive charge as well, so let's say I just put this up here, positive, these guys would experience a repulsive force. Now, these forces are identical in terms of unit and behavior. So, well, when I describe behavior, I mean like how they behave in terms of solving for them. Of course, obviously, attraction is different from repulsion. So, basically, we solve for them using Coulomb's law. And Coulomb's law, again, to reiterate from the last video, is given by the following formula. So, let's see screen. The force experienced by two charges is equal to Coulomb's constant times the absolute value of the magnitude of the first charge times the absolute value of the magnitude of the second charge over their distance squared. And again, Coulomb's constant, I hope you guys can remember this. Coulomb's constant is equal to 8.99 times 10 to the power of 9, or 9.0 times 10 to the power of 9. And their unit is in terms of Newton meter squared per Coulomb squared. Now, how can we analyze how the Coulomb's law works from this? So we're gonna shrink this down. We're gonna shrink the formula and we're going to prioritize Coulomb's constant. So hold on, let me just move this here. Let's do a unit analysis. Okay, I removed 8.99 because we'll be using 9 for the most of our computations here, just for simplicity's sake. So we know that Coulomb's constant is equal to Newton meter squared per Coulomb squared. And what's the value of force? We want to get newtons, right? And let's see how this plays into our formula. So charges are measured in Coulomb. So this is going to be multiplied by Coulomb, multiplied by another Coulomb, which can also be written as c squared. And this will also be multiplied by 1 over r squared. And r squared is in unit meters. So we have r times r, or meter times meter, which is also meter squared. So from this we can cancel out the coulombs, we can cancel out the meters, and we're left with Newton. And that's how we know that the Coulomb's law works. That is how we got the force between two charges. So now, let's get into actual problem solving and let's try to apply this. So I have two problems here, and let's start with the first one. So 2-point charges, Q1 is equal Q1 being 5 microcoulombs, this is microcoulombs, and Q2 being -3 microcoulombs, are placed 2 meters apart in a vacuum. Find the magnitude and the direction of the electrostatic force between them. So the first thing you want to do when you solve for any Coulomb's law problem is you want to draw the charges first. Here we have two charges, so let's just draw them. Doesn't really matter how far apart they are. I guess for realism, it's better, but doesn't really matter. So we know that the sign of the first one is positive, and you know the second one is negative. However, this is only a signifier. Really, it just tells us the polarity. Charges have no direction. So their sign does not mean that they're vector quantities. Charges are always scalar. Okay, so I'll just write it here. charges are scalar. So just don't forget that, because that's a commonplace mistake. Now, we also have their distance between the two. So we know that they're 2 meters apart. Do we know how they behave? So we have unlike charges, so they're going to be attracted towards one another. Now, here's another important thing to remember. Negative pulls positive. So the flow always of, or the direction that a charge wants to go to, is always from positive, or let's make this red. It's always going to be positive going to the negative. This applies as well in electric field. Alright? So here we know that they're going to be attracted to each other, but which one is going to which? We know that the positive charge is going to be going towards the negative. So we can just draw our arrow here. So actually we already know the direction, because there's only two charges. So we know that the direction is to the right. Now how about the magnitude? Now this is when we bring out our Coulomb's law. So recalling Coulomb's law, we have F is equal to K times the absolute value of Q1, absolute value of Q2 over R squared. Now I'm gonna shrink this because we're going to replace those values. Let's put that right here. It's our guideline. So our force is going to be equal, in this situation, we have 5 microcoulombs. So we have 5 times 10 to the power of negative 6. Micro is always to the negative 6, okay? And we have it multiplied to negative 3 times 10 to the power of negative 6. And we also have, we're running out of space, I'm gonna shrink this. There. And we also have 9 times 10 to the power of 9. And these two are all in absolute values, so that they don't have any polarity, or not polarity, rather sign. They don't have any sign. So our denominator will also be, is also given rather. We have 2 meters, so 2 squared. Now, how I like to solve it is all of the 10s are multiplied to each other. Because this is there, you can interchange these and it won't change anything. You can factor out the 10 basically. So using law of exponents, 10 times 10 to the power of negative 6 times 10 to the power of negative 6 is 10 to the power of negative 12. And then times 10 to the power of 9, that's 10 to the power of negative 3. So we'll have here on the numerator 10 to the power of negative 3. And 5 times negative 3 times 9. 5 times 3 is 15, because there's absolute value. So 5 times 3 is 15, times 9 is 135. This is all over 2 squared, which is 4. So now, what's our answer going to be? So we'll just plug this into the calculator. That's 135 times 10 to the power of negative 3. We have 0.03375. 0.03375 newtons to the right. And that's our answer for this question. So I hope this was clear. Basically, what we just did is we laid out the problem and we visualized it first. We know that the positive is going to the negative. So we're going to just plug in our values, and there we have our final answer. And of course, if for example we're looking for a missing charge value, you can always derive that from this formula. I don't have an example for that here, but try solving for one of these values by removing them, but you use the value of our force. See if that will work. And I promise you, it will. Okay. Now for the next question. Oops. Okay. This involves 3 charges now. And you want to get the net force on Q2 due to Q1 and Q3. Oops, there's a spacing error there. Sorry. But yeah. Okay, so let's visualize our problem first. We have 3 charges. Q1, Q2, and Q3. Q1 has a charge of positive 2. So we'll just signify that as positive. We also have another positive charge, which is Q3. And we have a negative charge in the middle. Now, how do we know that this is their arrangement? The distance in this problem is given in terms of x. So we can treat this as a number line where we're only going about the x-axis. Here, here, sorry, and then all the way here. There. So this is x equals 0. So actually this is the origin, not this one. This is 0 meters. Then the distance between this and Q2 is 3 meters. This is 3 meters. Is that x equals 3. And x equals 6 is the value or the distance value for Q3. So this is 6. And the distance between these two, again, is 3 meters. So that's how we know that this is their arrangement, going about the given. Now, we have 3 charges and we want to know how much force Q2 is experiencing and where it's going. So let's figure it out. Intuitively, we can say that it would be wherever the stronger charge is. So maybe we can say that it's going, if it were repulsive, it would be going straight to the left or whatever. Basically, just comparing the strength of the charges. However, we need to solve for it just to be sure. Now, this is where we use, again, Coulomb's law. However, now we have to split the problem into two. We have to split the problem into the force of this side and the force of this side. So the force of Q1 and Q2 and the force of Q2 and Q3. So let's just plug in our values here. They're in microcoulombs, so it's 10 to the power of negative 6 again. So we have 2 times 4 times 9. And we have again 10 to the power of negative 6 plus negative 6 plus 9. Again, this is from the law of exponents, okay? Just imagine that there's a 10 here. This is a shortcut, just so that we can keep our work tidy. Now, we have to divide by the distance between these two charges, so that's 3 squared. And we'll get 2 times 4 times 9, that's 8 times 9, 72. 72 over 9 is 8. And this is multiplied by 10 to the power of negative 3. This is also basically 8, then move 1, 2, 3. So this is our 0. We have 0.008 newtons. So this is our force for the left side of our problem. Now, how about the other side? So we just repeat the process. So we have Q2, which is equal to 4, because we have the absolute value again, right? Remember? So that's 4 times the value of Q3, which is 1, times 9. And this is multiplied by this again, and we know that that's equal to 10 to the power of negative 3. And we'll put that all over 3 meters squared. So 3 squared. 4 times 1 is 4 times 9, that's 36. Over 9, 36 divided by 9 is equal to 4. And that's times 10 to the power of negative 3. Or 0.00, oops, hold on, it's my computer, 0.004 newtons. Now, what do we do with these two numbers? This is when we start assigning directions. So, like we said earlier, positive goes to negative. So the left side, this charge, Q1, would be going towards the right, because the positive is going to the negative. Now, how about on the right side? The negative won't go to the positive, rather the positive goes to the negative. So this side is going to the left. And if you want to add signs just so that it's easier to visualize, or solve rather, the first half of our problem, Q1 and Q2, experiences a positive force, 0.008 positive. And the right side of our problem experiences negative 0.004 newtons, because they're going to cancel each other out. So if we add these two together, we'll have 0.008 plus negative 0.004, we would get a positive 0.004 newtons. And that means our final direction is to the right. And that is the final force experienced by Q2, as well as its direction. So to recap, basically we use Coulomb's law to determine the force experienced by Q2 on both sides. And once we have both sides, we simply add them with regards to their direction, or basically wherever they're supposed to be going. And once we figure out the directions and we add them together, the final sign is what we interpret to find the direction. So that's all for this video. Basically, Coulomb's law is something that we use to determine the electrostatic force between two charges. And we can use it to derive the value of one charge, the distance between charges, or again, simply plugging in the values, we can also get the force. So thank you everyone, and I hope this is clear. If there are any questions, leave them in the comments, and I hope that you guys will remember this law because you'll actually see it appearing a lot during Physics 2, or basically our electrostatics and electrodynamics concepts. So thank you everyone, and goodbye.